Lesson 1-2. More limits, continuity, IVT, graphing, adjustments. Here we go. If direct substitution does not give you an answer to a limit problem, because an indeterminate form is obtained, usually 0 over 0 is called indeterminate, use algebra to change the form so that you can evaluate the limits. So let's look here. If I evaluate at 0, 0 times anything will give me a 0 on the bottom and a 0 on the top. What we can do is remove the x and then reevaluate. This is called a removable discontinuity. The limit still exists. Plug 0 in now and you get the answer 1. Let's try it again. If I plug 2 in, it's 2 take away 2. That's 0. 2 squared, that's 4 take away 4. That is called indeterminate, 0 over 0. Because of that, we're going to use algebra to evaluate the limit. So another way is by factoring. So the denominator is called the difference of squares. So I can take the square root of x squared and the square root of 4. By doing that, I can remove the discontinuity, and then I re-substitute in. So plug 2 in and you get the answer 1/4. Number 3, if you plug 1 in, you get 0 over 0, which is a discontinuity. I can factor the numerator out. It's called a difference of cubes. So the cube root of x cubed and the cube root of 1. And then you square it, minus x. Is it minus? No, plus x plus 1. There's a little formula to it. I'm not going to stress out about factoring a difference of cubes right now. The x subtract 1's do remove. Now plug 1 back in and you get the answer 3. Number 4, a different way to do this. Again, when I plug 1 in for x, the square root of 1 take away 1 and 1 take away 1. It's indeterminate. That's the big word for the day. That's 0 over 0. No factoring. Because of the square root, we're going to use what's called the conjugate. So instead of the square root of x subtract 1, the conjugate creates a difference of squares. So you change the connecting sign and multiply. Now, because of that, the square root of x times the square root of x is x, and negative 1 times 1 is negative 1. In the denominator, I'm just going to put them beside each other. Is it still blurry? There it is. Now it's focused back in. So, because this is now a difference of squares, I can go first times first and last times last. Here it is. Now this is removed. Now you can evaluate at 1. So the square root of 1 plus 1, so that is 1/2. Number 5. If I plug in 2 here, I get 2 over 0. 2 over 0 is not indeterminate. This is simply undefined and this limit does not exist. Because it's from the right, you could write down on the right side it's going to infinity, but when it's at an asymptote, you can write down it does not exist. Number 6, discuss the continuity here. If I look here, what would happen if I plug 3 in here? Let's factor the numerator out. So that is x subtract 3 and x plus 1. I want you to notice that these are removable. When I plug 3 into the top and then 3 into the bottom, I get 2 different answers. Now, what happens here is there a hole in the graph? There's a hole at 3. So whatever the graph's actually going to look like, this is what the graph would look like. It's a line, x plus 1. So it starts at 1, and it's a line that goes up 1 and to the right 1. Now, at 3, there's going to be a hole. So normally at 3, the answer would be 4. But there's a hole there, and instead of the answer being 3, 4, remember, 3 plus 1, that's where that is. At 3, the answer is actually 5. So you have this line. The limit exists here because there's just a point that's out of place. So the left and the right both agree that the answer is 4 there. It's a removable discontinuity. That's the limit value, sir. But you can see it's not continuous. It's a removable discontinuity. Why is it removable? Because the limit exists. All right, if I look here, this is a continuous function. Find the value of a that makes it continuous. So if I plug 2 in here, I'm going to write it as a limit so we write it properly. So the limit as x approaches 2 of 3x squared plus a needs to equal the limit as x approaches 2 of the bottom. So what we're going to do is we're going to plug 2 in. 2 squared is 4, and 3 times 4 is 12. Plug 2 in, and I get negative 1. So a, when I subtract 12, is negative 13. That value would make these equal to each other, and if they're equal to each other, then it's continuous there. Number 8, use a calculator. So let's get our calculator out. So use a calculator to find limit. For this calculator, it's really easy. So we press menu, and then we press calculus, and then press limit. And then we type it in. We can do that. So type in as x approaches 1. And then that box is to write down plus or minus, if there's a little plus or minus, which there's not. Press Control Divide for a fraction line, and then type in x cubed, subtract 3x squared plus x plus 2. In the denominator, x cubed, subtract 2x squared minus x plus 2, and then just press enter. So this limit does not exist. That's what it means. We're going to do the same thing here. Is it the same function? It is, but as x approaches 2. So I'm not going to rewrite this all because it's exactly the same function. I just have to change the 1 to a 2. So I'm going to move this over, change the 1 to a 2, and just press enter. And this limit is 1/3. All right. Here I am. Intermediate value theorem. If it's continuous from A to B, and K is any Y value in between f at A and f at B, then there's at least one X value, or C, between A and B, where it equals that. And so if it's continuous and you have a Y value that's less and a Y value that's greater, if you have a Y value in between, there must be an X value where it exists because it's continuous. So if you don't lift up your pencil, you have a lesser value and a greater value. If you have a Y value in between, that's the intermediate value theorem. So if I look at 9a, first of all, it has to be continuous. So if I look at x squared subtract x, it is continuous. It's a parabola. Then I'm first going to plug in f at 0 first here, and I get 0. If you plug in f at 5, 5 squared take away 5, that's 20. This answer is in between that. So if that y value is in between that, there must be an x value that exists to give us that answer. So we take the 12, we make it equal to the function, and then we solve it. So we're going to make it equal to 0. We're going to factor it. So that's negative 4 and positive 3. And then when I solve it, each factor has a solution. So positive 4 and negative 3. We just need to be careful of the domain restriction. So we're looking for an answer between 0 and 5. So negative 4 can't be it. So the only value that would satisfy the intermediate value theorem would be positive 3 because it's between 0 and 5. For B, between 0 and 3, there's a discontinuity at 2. 2 take away 2 is 0. It's not continuous. 2 is in that domain restriction, right? 2 is between 0 and 3. So the intermediate value theorem does not apply because it's not continuous. So it doesn't apply because at x equals 2, it is a discontinuity. So it must be a continuous function in that domain restriction for it to apply. It says find the value of c in example 9a. I just did that. So all that work would go right here in terms of what's happening. So I doubled up there ahead of time. Parent graphs. You know these. A line, a parabola, a cube function. X to the fourth is like a parabola. Square root of x, cube root of x, x to the 2/3. I think it looks like a seagull. The absolute value of x. A v, 1 over x, a reciprocal function. 1 over x squared as a reflection of this so that both ends go up in the middle. We have a circle. We have a sine function. It starts in the middle and goes up. Cosine starts at the top. So these are all basic pre-calculus functions that we need to know and can apply if we have to. All right. So different graphing adjustments. We know a negative in front is a reflection and a negative inside is a reflection. One is the x, one is the y. If you add or subtract outside, it goes up or down. Add or subtract inside, it goes in the opposite direction when it's inside. Multiplying creates a stretch or compression. Absolute value reflects points. This one's the tricky one. If it's the absolute value inside, you only graph what's on the right of the x-axis and then reflect over. All right. Use the graph here to be able to do this. So this says shifted 2 to the left. So all the key points will be shifted 2 to the left. So that's at -2. So I'm going to find -4. A little bit off my graph. So -4 and 2. Here, shift it. That's -3 and 0. 0 here, shift it to the left 2 is -2 and 2. So here's the parabola looking part. And then the last part is shifting this here. So this is 3, -1, so shift it here. So it becomes 1, -1. And then connect. All right. Number 12. So there's a reflection. This negative means it's been reflected across the x-axis. And then you go up 2. So if I reflect this and go up 2, -2, 0. If I reflect it, it stays here on the axes, and then we go up 2. Here, reflect, it goes to -2, and then up 2, it's 0. So it's going to be, this is what the reflection does to the parabola. And then here, reflect it, so it goes here to 1, and then up 2 goes to 3. So 3, 3. Oops, there's 3, 3. All right, let's see if we can keep the graph and what I'm doing here at the same time. So this is a reflection and compression. So it's going to reflect on the x or on the y-axis, and then it gets compressed, the y value. So it gets compressed down. So I'm going to reflect it over, and then it gets compressed. So if I reflect it over, and then half the value, I get right here. So at 1, 2. If I do here, if I reflect, and then half the value would be right here in the middle. Here, you can't reflect on the axes, and then half of 0 stays 0, so that one's going to stay the same. Here, if I reflect it, it becomes -3 and then -1/2. Oh, wait a second. I get a half the y value. I didn't do that. Let me try again. So we're going to reflect and then half the y value. So it's right here. Sorry. So 2 and 1. Silly me. I make mistakes. So reflect and then half the y value. Can't reflect, but half the y value puts it at 1. Oh, here. This one. So I can reflect and then half the y value is 0, so it stays at 0. It's right here. This one, I can't reflect, but half the y value is at 1. And then here, reflect, and it's -3, and then half the y value is at half. I can get there. I don't give up easy. Here it is. Number 14. So absolute value means anything negative gets reflected up. 2x actually means you half, it's the inverse, you half the x value. So for -2, half of it, in terms of it, it becomes -1. So -1 into half the x value becomes -1/2. Half the 0, it just stays there. And then this part here of the line, if you half the x value, this becomes 1. And this becomes 1/2, but it gets reflected up. So it's 1/2 and 1. One more. I know these are a little tricky. When the absolute value is on the inside, you only graph what's on the right side and then reflect it. So just graph what's to the right of the axis. So at 2 and at 3 and -1, and then you just reflect this over. So if I reflect it over, I need to find -3 and -1, and that's it. All right, number 16. That's it, number 16. All right, there's your lesson. Mr. G Math over and out, and then we'll do the assignment together.